Morning friends. We are studying the first chapter, that is network theorems. This is presented by me, Hanumant S. Pichatti, lecturer in Government Polytechnic, Mudud. So in this chapter we'll be studying introduction. That's just a revision of the basics what you have studied in your previous semester. Next, Thevenin theorem, Norton's theorem, superposition theorem, and maximum power transfer theorem. Now in today's class, so we'll be studying about introduction, that is revision of your basics. So here we'll be mainly studying network terminologies, Ohm's law, Kirchhoff's voltage law, Kirchhoff's current law, voltage division rule, and current division rule. First, let us take network terminology. So mainly we'll be studying four terminology here, that is a branch, a node, a loop, and a mesh. So branch is something that is it represents an element in the network. So it will have terminals. So any element which has terminals it can be termed as a branch. Now, node is many branches are connected at a point is called as node. So two or more branches can be connected, and that point is called as node. Loop is any circular path or any closed path in the network is called as loop. Closed path means you have to start from that point and traverse through the network and coming back to the same point is circular path or closed path. That can be termed as a loop. Mesh is also a loop, but it has got something specialty. So mesh is also a loop which doesn't have any loop inside it. So it cannot be reduced further. So a loop in which another loop doesn't exist, that can be termed as a mesh. Now here in this picture you can see all the terminologies. So I have four branches here. I have four elements, network elements connected in parallel. You can see in the diagram there is a current source, a voltage source, and two resistors. All of them have been connected in parallel. Now since all of them have been connected in parallel, their ends have been tied to two places. So if I take four elements and tied together, so at the top you will get a 1 point, and at the bottom also you will get 1 point. So these points can be termed as node. Now here in this diagram you can see node A and node B, and each element can be termed as a branch. So here four elements are there, so hence four branches are there. And in this clearly you can see what is loop and what is mesh. So in the loop, so you can take a longer path traversing from a resistance to voltage source and through second resistor and going back. So that can be a loop. But mesh is also a loop, but it has one speciality, that is another loop does not exist in this loop. So here in this diagram you can see in the first block that is a mesh, since there isn't any loop inside it, so that can be a mesh. So second one is a loop. So in the loop you can see there is one more loop, but loop in the loop, another loop can exist but not in the mesh. Hope it is clear. Now one more important thing you should know, you already studied this, that is in a series combination or in a series circuit, current is same through all the elements but voltage drop across each element is different. Similarly, in the parallel connection, voltage across each element is same, but current will be divided among them. Now first, let us see what is there in the Ohm's law. A famous physicist, George Ohm, found that at a constant temperature, a current carrying conductor, if a voltage is applied across its terminal, a current through that conductor is directly proportional to the voltage applied across it, and it is inversely proportional to the resistance offered by that conductor. So in the equation form, you can write current I is equals voltage V divided by resistance R. So that you can see in the slide. Now something interesting, that is Ohm's law triangle. So in this triangle I have taken three quantities, that is voltage, current and resistance. Voltage has been placed at the top corner and current and resistance have been placed at the bottom. Now if I want to find out voltage, so from the Ohm's law I got that V is equal to I into R. How can you find it from this triangle? So in the first triangle you can see, if I want to find out the voltage which is at the top, keeping that quantity is at the left side, the right hand side you can write. So when I take that top quantity, you are left with another two quantities, that is I and R, so which are side by side. So I can easily write V is equal to I into R. Similarly, going to second triangle where I want to find out the current I. Where is current I in this triangle? So current I is at the left corner. So I'll keep that at the left side equation, and that's I is equal to, so where keeping that apart from that quantity, what are all there? V and R. So where they have been situated, V is at the topmost corner, R is at the rightmost corner. So I can easily write I is equal to V by R. Similarly, going to third triangle, so in which I want to find out R. So R is equals, so if when I take R at the left side of the equation, so I am left with the V and I. So I can easily write R is equal to V by I. So with this triangle you can easily remember this equation and conversion from one form to another form. Let us take an example for this Ohm's law. For the circuit shown in this slide, find the current I. So when you look at the circuit, it has got one voltage source of 24 volt and a resistance of 12 ohm, and it's been asked to find out what is the current that is flowing through the circuit. Now from Ohm's law, I is equal to V by R. So what is V? 24 volts. What is R? 12 ohms. So 24 by 12 is equal to 2 amps. So like this you can find out any quantity if you know another two quantities. So that is, if you know I and R, that is current and resistance, you can easily find out what is voltage. And if you know V and I, that is voltage and current, you can easily find out what is the value of resistance. Now, one more important law, that is Kirchhoff's voltage law, which states that in a closed loop or a closed path, algebraic sum of the all the voltages and voltage drops is equal to 0, provided you have taken with a proper sign. And this law states about conservation of energy. So in a closed loop, we treat that as energy is neither created nor lost. So that's why we're equating it to 0. Now let us consider a network here, consisting of voltage source Vs, resistance R1 and R2. Now can you apply our KVL here? Yes, of course you can, so since it contains a closed loop. Now I told that these voltages has to be taken with a proper sign. So how we can take that? So if you are traveling from a negative terminal to positive terminal, that voltage is taken as positive. And if you are traveling from positive terminal to negative terminal, then that is taken as negative voltage. Now let us start from the voltage source Vs. I'll start from the negative terminal of Vs and move to the positive terminal of Vs, and then through R1 to R2, like 7, moving through the loop. So here from in the Vs, I am traveling from negative terminal to positive terminal. I will take it as positive Vs. Going next to resistance R1, wherein I am moving from positive terminal to negative terminal. Hence, I have to take this voltage drop as negative. That is, how we can find out voltage drop? That is I into R, that is current into resistance, that is minus I into R1. Similarly, in the resistance R2, what is the value of voltage drop? Since I am moving from positive terminal to negative terminal, again I will take it as minus, and voltage drop is equal to I into R2. So in the equation you can write that is Vs minus I R1 minus I R2 is equal to 0, or Vs is equal to I R1 plus I R2, or I is equal to Vs by R1 plus R2. So by like this we can easily find out what is loop current, what is branch current. So this KVL is very helpful in finding out loop currents and branch currents. Now one more important law is given by Kirchhoff's, that is called Kirchhoff's current law. Now in this law it states that sum of the currents entering the loop is equal to sum of the currents leaving the junction. It states about conservation of charges. So charge is neither created nor lost, or charge doesn't have any path for loss. So here I am taking a junction here. So you can see in the picture that at junction I1 and I2 are the current entering to that junction, and IT is the current that is leaving from that junction. So from KCL we can easily write IT is equal to I1 plus I2. So next is voltage division rule. So these voltage divider circuits are used to produce different voltages from a common source. Now here in this circuit, I have a voltage source Vs and two resistance R1 and R2 which have been connected in series. When I say series, so one thing you should remember, that is in the series path current is constant or same. Now, can you apply KVL to this path? Yes. So what is that? So Vs is equal to VR1 plus VR2. So what is VR1 and VR2? Those are voltage drop across resistance R1 and resistance R2 respectively. So VR1 is equal to I, that is current flowing through the circuit, into resistance value R1. And what is VR2? That is I into R2. Now what is I in this case? So you can easily find out what is I. I is V by total resistance. So total resistance is, since R1 and R2 have been connected in series, that can be taken as R total resistance equal to R1 plus R2. What is the applied voltage? Is Vs. Can you find out current? Yes. I is equal to V by R, that is Vs divided by R1 plus R2, that is total resistance. Now Vs is equal to IR1 plus IR2, that is equation number 1. Can you find out voltage drop across R1? That is VR1 is equal to I into R1. We have already discussed what is I. I is equal to Vs divided by R1 plus R2 into R1. So, and I'm just rewriting this, that is VR1 is equals Vs into R1 divided by R1 plus R2. So I call this as equation number 2. Similarly, can you find out the voltage drop across R2 in the same manner, that is VR2 is equals I into R2. What is I? It is Vs divided by R1 plus R2 into R2. Now I will write VR2 is equal to Vs into R2 divided by R1 plus R2, that is called as equation number 3. Now can you observe these two equations, that is equation number 2 and equation number 3? That is voltage drop across resistance R1 is given by source voltage into that resistance R1 divided by total resistance R1 plus R2. Similarly, voltage drop across R2 VR2 is equals source voltage into resistance R2 divided by total resistance R1 plus R2. So that is voltage drop across any resistor connected in series is given by Vrx is equals Vs into Rx divided by R total. So what is Vrx? That is voltage drop across that resistance. What is Vs? It is supply voltage. And Rx is the resistance at which we want to find out the voltage drop. And R total is the total resistance of a series path. So by using this formula, you can easily find out what is the voltage drop across each resistance in the series path. We have one more rule, that is called as current division rule. So using this rule, you can easily find out what is the current entering in each parallel path. So we have learned that in the parallel combination, voltage is same across all the resistances. So there is IT is equals IR1 plus IR2. So here applying KCL at this junction, there is IT is the current entering and IR1 and IR2 are the current leaving. So I can write IT is equals IR1 plus IR2. Now can you find out voltage drop across R1 and R2? Yes, you can easily find out. That is IR1 is equal to that is current through resistance R1 is equals V divided by R1, and current through resistance R2, that is IR2 is equal to V by R2, since V is same in the parallel path. So total by KCL we have written IT is equal to R1 IR1 plus IR2. So I can write IT is equal to IR1 plus IR2. I'll just replace this IR1 and IR2 in this equation. That is IT is equals V divided by R1 plus V divided by R2. So I'll just take this V as common. So then I have remained with 1 divided by R1 plus 1 divided by R2. So that is IT is equals V into R1 plus R2 divided by R1 into R2. There I have just taken an LCM. So I'll just rewrite this equation as V. So V is equals, I'll take this part into that side, that is IT into, so the one is at the denominator will move on to the numerator on the other side. So IT into R1 into R2 divided by R1 plus R2. So I'll call it as equation number 2. Now solving for individual branch current, that's IR1. So what equation we have written for IR1? So IR1 is equal to V divided by R1. So we have found out what is V here. Just substitute this value into this equation. That is IR1 is equal to V divided by R1. So what is V? It is IT into R1 into R2 divided by R1 plus R2 divided by R1. So when you divide this by R1, what we will get? So that is IR1 is equal to IT into R2 divided by R1 plus R2. I'll call it as equation number 3. Similarly, IR2 is equals V divided by R2. So again I will replace V value here. What is it? IT into R1 into R2 divided by R1 plus R2 divided by R2. So it cancels R2 and R2. So I remain with, that is IR2 is equal to IT into R1 divided by R1 plus R2. I call it as equation number 4. And can you observe equation number 3 and equation number 4? So here equation number 3, that is current through resistance R1 is equals total current into R2. For R1 I am getting R2 resistance, that is total current into R2 divided by total resistance R1 plus R2. Similarly, equation number 4 is current through resistance R2 is equals IT into R1. So here for R2 I am getting R1. So I total into R1 divided by R1 plus R2. So that's what the current division rule says. So current through any resistance connected in parallel is given by IRX is equals IT into RX divided by R total. So where IRX is the current through any resistance that is connected in parallel. IT is supply current or total current, and RX is resistance that is opposite to the resistance at which you want to calculate the current. In the current division rule, you should remember this. In the current division rule, we are taking an opposite resistance. In the voltage division rule, we are taking the same resistance. That's what is the difference. And R total is the total resistance in a series network. When if they have been connected in series network, what will take R1 plus R2 will take the same thing. So what all we have studied in this? We have studied network terminology, Ohm's law, Kirchhoff's voltage law, Kirchhoff's current law, voltage division rule, and current division rule. Hope this is helpful. Thank you.